Okay, so this video serves as an introduction to our package JointNets. It will start with the motivation of building this package and what it aims to solve. Then some background knowledge will be presented to facilitate understanding. Afterwards, the package is going to be broken down into modules, and each module will be discussed. Towards the end of the video, I will also show some results and demonstrations of the package. This video will not cover much mathematical background of graphical models, and it serves only as an introduction to the package functionalities. As the package is being updated, the video might get outdated, but it should at least provide a nice overview of functionalities. Please refer to the materials and the links under this video for more information about JointNets. So let's get started. JointNets, let's put it simple, it's an R package that provides the tools to learn undirected graphical graphs from data. These graphs indicate dependency structures among data variables. As the methods implemented in this package imposes Gaussian assumptions on data distribution and sparsity constraints, the generated graphs are named sparse Gaussian graphical models. Why do we care about generating graphs from data? These graphs actually have broad implications and have been studied in many fields. Take neurology as an example. Research scientists spent decades seeking both connections between different brain regions. Combining sparse Gaussian graphical models and neuroimaging data results in predicted functional brain connectivity, which might indicate surprising patterns of our brain. Moreover, recent advances in sparse Gaussian graphical models makes graphs even more powerful. Multiple graphs can be estimated simultaneously from multiple related datasets. Fast estimation of difference graphs is possible and creates potential for efficient classification tool. Expert knowledge such as partially known dependency structures can be incorporated in the estimation process to improve graphs as well. However, there is a lack of toolboxes to provide a unified interface for these powerful methods. Existing source codes and packages often don't agree with each other on data input formats and output formats. Moreover, most of the available toolboxes perform only limited functionalities, mostly on estimation and visualization, ignoring evaluation and applications. As a result, building a comprehensive and unified package becomes an emergent task, and JointNets provides exactly that. I have talked briefly about graphical models, and most of you probably still are confused what exactly it is. Thus, before delving into what JointNets are capable of, I would like to first present some more background knowledge with some visualization results to ensure you understand what the main task really is. For Gaussian graphical models, as an assumption, the data samples used should follow multivariate normal distribution. The computed dependency structure among variables are organized in the matrix. Due to the Gaussian assumption, such matrix becomes symmetric and is named the precision matrix. Also is the inverse covariance matrix. Precision matrix can be naturally viewed as an adjacency matrix, and non-directed graphical models can be easily obtained. Sparse Gaussian graphical model methods work with data that are high-dimensional, meaning the number of observations can be smaller than the number of dimensions. As a result, the estimated precision matrix is sparse, meaning most entries are zero, representing no dependency structure between two nodes. Also implies that no edge between two nodes are in the graph. To visualize graph generation process, let's look at a list of data samples here. Each data sample has p dimensions or variables, and we have a total n data samples. We can then organize them into a data matrix of dimension n times p. As explained before, our graphical model methods would estimate a p times p precision matrix and further a p-node undirected graph. Note here, due to our Gaussian assumptions, Precision matrix is not simply correlation matrix imputed from the samples. It is indeed the conditional correlation. In this slide, we can see the node 1, 2, and P are correlated, as there are edges between them. However, in reality, node 1 and node 2 is correlated because node P's contribution. Thus, in a conditional correlation case, node 1 and 2 are not conditionally correlated given P. Our estimated graphs thus will get rid of extra correlations that are not informative. As for joint estimation, we have both estimate multiple graphs from multiple data matrices as well as estimate difference graphs from two data matrices. So difference graphs contains edges that are not shared between two graphs. As we can see here, we have a list of data matrices. We have different data matrices from different contexts. Each matrix has dimension sample times attributes. Note here we have different number of samples for different contexts, actually. Our method is thus able to produce multiple graphs from the above data. Note here that we assume only two contexts, and two contexts indeed have different connections among nodes. As a result, for joint estimation of multiple graphs, we would visualize it as a single graph with each edge colored to its own context. The shared part represents edge that exists in both contexts. On the other hand, for representing difference graph, it is simply a single graph containing all the edges that are distinct to both contexts. JointNets' main functionality is to provide options for graphical model estimation, and thus we have incorporated state-of-the-art estimators to perform various tasks. We aim to ensure various datasets, constraints, and estimation types will find suitable estimators in JointNets. Joint Graphical Lasso is the main baseline incorporated in the package. Climb and EE are estimators that our algorithms build upon and not currently supported. Over the years, our lab has developed graphical model methods including FastShame, Geek, Simu, WSimu, Diffie, and Diffk. These are the main methods that are all encapsulated in JointNets. These methods range from joint estimation to difference estimation, as well as imposing constraints. More details on the algorithms, please refer to the end of the video's reference section. JointNets' ultimate goal is to provide an end-to-end unified framework for sparse Gaussian graphical model learning, and we believe we have achieved that. The package is broken down into 5 modules, with the simulation and evaluation module being the primary ones to test for graphical estimation against chosen methods and simulated datasets. Estimation module contains the core methods to perform the estimation. Visualization offers fast and customizable plot of graphs. Classifications allows users to easily apply graphical models for binary classification tasks. The flowchart on the right shows how these modules are tightly connected, as simulation is the start point and evaluation serving as the ultimate goal. In the following slides, I will be discussing each module. First, it is the simulation module. The primary functionality is encapsulated in the function simulation. It serves to generate both sparse graphs and samples with user-given parameters. The simulated graphs and samples can be used to test against method effectiveness, visualization, and etc. A number of parameters that are required for the method to properly function. The first, it is the sparsity parameter for both shared and individual graphs. User can input a number between 0 and 1, with 1 representing the least sparse. Dimensions, or the number of nodes in the graph, is also required. User also inputs the number of contacts for the generated graphs, which is an integer representing how many related graphs will be simulated. Samples is a vector of integer, representing the number of samples desired for each context. This module is able to allow users to simulate a wide range of datasets and their corresponding graphs. Estimation module is the core of JointNets package, as the package incorporates many algorithms or different types of estimation, record, simu, diffie, and etc. Each method is encapsulated in a single method named with their acronym. Since methods vary from each other, parameters can vary drastically. Here I will be only talking through some universal parameters. So first there is the correlation option. User can pick from Cove and Candle. Cove computes the empirical covariance matrix from your given dataset as the start point for estimation, while Candle computes the candle-style correlation matrix at the starting point. Intertwined is the option user can control with true and false. Intertwined enabled means that individual covariance correlation matrices are computed under the influence of the main covariance/correlation matrix. Inputting prior knowledge is also available in some of the methods, for example WCMU. User will be able to input a matrix representing known sparsity patterns of the graph to guide the methods towards it. So all the methods will output a list of results, and please refer to the GitHub or the actual package documentation for more details. The flowchart on the right shows how users can select the appropriate methods for their desired graphs and specific dataset. Generated graphs need to be visualized. Thus, in the JointNets package, user has a variety of options to visualize generated graphs from the estimation module. A single plot function inherited from the generic plot from R allows users to plot generated graphs. As oftentimes generated graphs contain multiple contexts and many nodes, we offer options for users to create unlimited choice of subgraphs, such as selecting certain contexts, certain nodes, or even predefined layouts. Title and legends are included in default to help user differentiate contexts based on colored edges. All default options can be customized by overriding existing parameters. Plot Brain is a special function to plot brain graphs in 3D space with the brain overlay. We realize graphical models huge implication in neuroscience, and thus we offer this function for scientists to quickly visualize brain connectivity. The generated graphs are interactive as users can freely rotate and zoom. Evaluation modules helps user to evaluate generated results from the estimation module. If ground truth is given, F1 and AUC scores can be computed. The big score provides a metric for users to assess model validity without ground truth. Classification module allows users to utilize graphical model for real-world applications. As classification is implemented with quadratic discriminant analysis, to predict a single data sample from its context, the function QDA can be called. QDA eval runs QDA for multiple data samples and provides an accuracy rate measure and other evaluation metrics as the result. JointNets is loaded with datasets for users to explore how graphical model estimators perform. There are two data sets of simulated data of dimension 20 and 100. Low-dimensional and high-dimensional genomics data is also provided. Natural language text data is pre-processed from the NIPS conference WordCon dataset. Brain imaging data pre-processed from the BI dataset is also available as well for users to see brand visualization in action. Here are some ready-made visualization results. The 2D one here is a visualization of the text dataset. We're able to see that certain words exhibit dependency structures such as neural and network, distribution and probability. Red edges represent dependency structures exhibited uniquely in the first context, and blue edges represent dependency structures in the second context. Green edges are the ones shared among two contexts. On the right, there's a 3D brand visualization plots. It plots the graph with a brand overlay. It is shown on the right, and it has the same legend format as the 2D case. Here are some experimental results user could generate from the evaluation module. As AUC function provides true positive rate and false positive rate, user can easily plot an ROC curve to view how different methods perform under different parameters. Here are some more experimental results to prove that the state-of-the-art methods implemented in JointNets achieves good results for classification. JGL is the baseline here we're comparing to. JointNets comes with many demonstrations. After installing it with R, simply type demo. You will be able to view a list of demos that are available for JointNets. Then users can view the demos by typing demo with two brackets with the demo name within the bracket. There's also an R markdown file that I wrote, which is available on the GitHub link under this video. As a conclusion, JointNets indeed achieves the purpose of making the package end-to-end. It expands beyond simple estimation and incorporates simulation, evaluation, and even application. Graphical models are interdisciplinary tools, and I hope this package is able to show how different fields can all benefit from this powerful model. All APIs returned are highly scalable, and new methods and visualization ways can be easily added. And some future works to be done for this package. The first one is to incorporate different models for classification in order to extend beyond binary ones. Also, to make sure the package is easily accessible, a full GUI could be greatly helpful. So here are some references for the algorithms implemented in JointNets, as well as some Gaussian graphical model related materials. Thank you.